So that's my introduction to the session. So we can start with a keynote by Mr. Stefano Monti. I do not give his CV in detail. He's currently, you have been already introduced, but just to remind, he's still the section head of IEA since 2015. Please go.
So good morning, everybody. First of all, I hope that you enjoyed your breakfast. And I'm going to talk about global trends in nuclear power. Actually, this is a session devoted to safety, and there is not a lot of safety in my title. Thank you very much. But of course, coming from the IEA, it will be pretty easy for me to refer to safety-related activities in support of what I'm going to present, which is somehow related to advanced reactors, and in particular small modular reactors. But starting from some global trends on nuclear power in the world. I'm sorry, I'm from UN, so I will not focus very much on Europe. I will talk about the global trends, which anyway, affects also the decision in Europe. And from this point of view, this presentation is a kind of follow-up of my presentation yesterday, when I was trying to put nuclear power in the frame of the clean energy and decarbonization of in particular of the electrical sector. And when I was saying that the situation regarding affordable and clean energy in the world is not so good, I was basically referring to this graph, in which we see that still nowadays, more or less 70% of the electricity is being produced by fossil fuel, and the situation regarding the so-called clean energy remain more or less the same since long. It is somehow 35% of the overall production, and at the end of the day, the impressive deployment of new renewables, when we consider that at world level, accounts only for 2%. So the impressive deployment actually happened only in some part of the world, and overall their weight is still pretty low. And at the end of the day, since we know that actually nuclear power was some 17% of the whole pie before Fukushima, nuclear has not been replaced really by renewables, at least globally. It has been replaced above all by gas. Okay? And coal is still the primary energy source for electricity production. Well, hydro is stabilized more or less at 16%, because we know that more or less we are at saturation for that. And if you look at the trends, this also reflects what I was saying yesterday, that coal is still the major, over the year was always the major primary energy source. Now it's a little bit flat, so it seems that we have at least a reduction in the derivative in the use of coal. But again, this is being compensated by natural gas. So the real winner is gas. Okay? It's still, a fossil fuel production, so I don't think that we can really consider natural gas as a real clean energy to be accounted for in that part of the electricity production. Nuclear is here. The overall amount of the absolute amount of electricity production by nuclear is more or less stabilized since a number of years, but in percentage, of course, there is a decrease, because you can see the overall production is really still increasing, and it will increase even in the future. This is also the expectation, and this is why when we talk about clean energy, we always refer to electricity, even if, of course, it's only a part of the whole package, because the whole world is moving towards electricity production. So first of all, we have to decarbonize the electricity production. About nuclear, well, this is an interesting graph which has been realized using the data from our PRIS database, the database which provide the information on all the nuclear power plants in the world. The trends, reflect what we have in mind on what happened in the world. So first of all, of course, these are the bar corresponded to the number of nuclear power plants which were put in operation in different years. Okay, so the trends is pretty known that there were a period around the 70s in which there were even up to 37 nuclear power plants connected to the grid in a single year, and it corresponded to the oil price shock in the 70s. There was a 3 Mile Island. Actually, if we consider the realization after 3 Mile Island, there was not a big shock, a big sharp decrease, because at the end of the day, the nuclear power plants that were already under construction, most of them were put in operation. The real shock was, of course, after Chernobyl, and this is the clear trend, in particular in OECD countries. Then some attempt to, the so-called nuclear renaissance that we heard about just before Fukushima was actually above all in non-OECD countries, in particular China and India started to build nuclear power plants. And then another shock was clearly Fukushima. So people that they say that in some international context, I heard that at the end of the day, Fukushima was not such an impact on the nuclear industry. It's not true at all. We had an impact from Fukushima, which demonstrated that, of course, safety is of primary importance if we wanted to keep nuclear in the package and in due consideration for our target regarding climate change mitigation and so on and so forth. And these curves are also pretty interesting. Here is the percentage. This is the percentage of nuclear on the overall package over the years. And this is the case of OECD country, where there is a clear decline in using of nuclear power. Here in this is the whole world, okay? And this is non-OECD country. So also in non-OECD country, when we consider the percentage with respect to the overall electricity production, I mean, nuclear is still at some 5%. Of course, this decline in the use of nuclear power can be even worse when I come back to the same slide that I showed yesterday. If we consider aging of nuclear power plants, above all in developed part of the world, in Europe in particular, and in the United States, more than 80% of nuclear power plants currently in operation are over 30 years. So of course, if we don't extend the life of this nuclear power plant, of course in a safe and secure way, well, in this part of the world, there will be a clear, sharp decline in the use of nuclear power, and this is why it's so important, of course, to proceed with the life extension of this reactor, which means, of course, on one side, nuclear power innovation, that I mentioned specifically yesterday in my presentation. On the other side is, of course, to put a lot of effort, because at the end of the day, we would like to have the so-called Gen 2 reactors as safe as the most advanced Gen 3 and 3 plus reactor under construction or first operation in these last years. And this is a challenge, okay? So, of course, the whole nuclear community should put really an effort in maintaining the current fleet in operation, but of course in a safe, secure, and well safeguarded manner. Well, if we consider now the trends are not really very optimistic. There are 54 power reactors under construction, and there are some 30 countries considering introducing nuclear power for the first time. These numbers are important because then, I mean, if they are under construction, then we have to look at this curve, what will happen in terms of connection to the grid in the coming years. With these numbers, we will never reach this part of the graph, okay? Because if there are 54 now in construction in the world, they will be connected, of course, in different time over the most probably the next optimistic 6, 7, 10 years. So, of course, the number of nuclear power plants connected to the grid can be in the order of 7, 8, 10 nuclear power plants per year. And for sure, this trend is not sufficient to contribute in a significant way to this, sustainable goals that I was mentioning yesterday. And when I say that energy is really at the centerpiece of the 17 UN SDG, I was referring to that for instance, there is 1 billion of people that they have no health care because of energy poverty, because there is a lack of energy. So this is why it's so important to keep the track of the clean and affordable clean energy, because it really is enable the achievement of all the other SDG goals. Where are these nuclear power plants under construction worldwide? Well, we know we have China with 11 under construction, which, by the way, is a lower number that they had in previous years. We have 7 in India, 6 in Russia. We know the case of Europe, Finland, France. We already put the UK, hopefully, and then Slovakia. These are the European case. And what else? Well, this is another, in my view, interesting, say, numbers, which again shed the light on where it's possible really to deploy nuclear power plant. Well, you can see here, okay, there are 54 nuclear power plants under construction in 19 countries, okay? But at the end of the day, okay, there are 14 developing economies, so most of them are in non-OECD countries, and 40 in state-owned operator, okay? 47, sorry, okay? So, and only 1 in a pure, what we can consider a pure deregulated market. So, this confirms what we have already stated, that nuclear power for sure requires a very strong state support with the adequate incentives. Otherwise, it will never fly. The major issue remains, of course, to mobilize private investors, and the real reason is that nowadays to propose a big project in the order of 10 billions, 20 billions with time to return of the order of 10, 20 years is really challenging. And from this point of view, small modular reactor, unless we really invent new financial schemes, are not very different. I just wanted to remind you the case presented in the MIT report, which was kind of a very well-known document published by MIT a couple of years ago. And it showed also the case of NuScale, one of the most advanced small modular reactor under licensing in US, in which, for instance, for the deployment of the first of a kind, there is the need of an investment of some $5 billion. And then with some mechanisms that they have put in place, with some lending money, etc., from the DOE, they can reduce this investment, this private investment at the level of 3.5. But the point is that the time the return from investment still remain in the order of 19, 20 years. Okay? So at the end of the day, it's not the problem to find 5 billion euros. I mean, I always say the world has never been reached as today. Okay? When there are private companies that they have a capitalization of 1 trillion, I cannot even pronounce. It's not so difficult to find investors which are able to provide 5, 10, 20 billions. The point is that when you tell these people that they will return from their investment in 20 years, they look at you, are you crazy? It's not clearly possible. Okay, so on one side, it's clear that nuclear power needs a clear policy at governmental level, and of course we have also to work in a creative way, I would say, on new financial scheme which can favor mobilization of private investors, private investment. Situation in newcomer countries, this is always an interesting part of the picture because, of course, it gives the trends out of the classical nuclear country, which have installed nuclear power plant in the last 40, 50 years. The situation is pretty known. The one which are really closer to operation are the UAE, Bangladesh, Belarus, and Turkey. They are full committed on nuclear power. They have found a way, of course, with some particular financial schemes to go nuclear. They are all supported by the International Atomic Energy using our milestone approach. However, again, the situation in the newcomer countries also shed a light on the importance of one of the most important factors which remain in the nuclear power, which is the human capital. Okay? Because look at the case of UAE. It is not about technology. The technology and also let's say the management of the project was perfect. The reactors were built and let's say brought to commissioning, to almost commissioning on time and on budget, which is not trivial nowadays. But now, I mean, they lag behind. They cannot really start operation. Why? Well, because they don't feel enough ready in terms of human resources and operators to manage the reactors. Okay, so at the end of the day, this also gives another important message to all the nuclear community. On one side, there is a safety. On the other side, there is the effort, the continuous effort on capacity building and human resource development. Nuclear is a mature technology, but it remains still challenging above all for countries which don't have a solid tradition in nuclear, and it requires a lot of effort from the education and training viewpoint. About the rest of the numbers, there is another countries. We are not allowed, since these come from a categorization, internal categorization of so-called newcomer countries, we are not allowed to put the name of the countries related to these numbers. Is considered confidential because, of course, there are also political issues related to the fact that we consider a country in phase 0, 1, 2. I mean, more closer or less closer to a real deployment. However, these are this one is known as Egypt. And then there are these countries we can really think that they're the one which are preparing the infrastructure. Infrastructure in terms of IEA means everything, including human resources, including the adaptation of the legislation in order to go nuclear, in terms of putting in place a suitable nuclear regulatory body, and so on and so forth. So infrastructure is in the broader sense. And since they are spending money, even a lot of money, putting in place the infrastructure, we think that these new four are really committed and will go nuclear. Sooner or later will go nuclear. On this part, well, this one, when they say active preparation for final decision, it means that, for instance, the state is taking some step from the infrastructure viewpoint, for instance, considering the fact to put in place independent nuclear regulators in terms of course, modification to the legislation and so on and so forth. And 9 are only considering nuclear. So they have, I mean, expressed openly that they want to consider nuclear. And one of the reasons to do that is, for instance, because they took obligation in terms of climate change mitigation. So, of course, they see nuclear power as one of the means to address their obligation for the climate change target. And this is an important issue, in my view. It's a message that is important for the rest of the nuclear community. There are, not only, also for the whole world, when people say that nuclear power is actually a transition technology, is not something which can be considered for the future. Well, if you consider that when you adopt nuclear power, you commit your country at least for other 100 years, actually, if you consider also the high-level waste even more, this is not true, because there are countries, I mean, like for instance Bangladesh or Egypt, that they will come to our conference in October, and they will state clearly that they are committed to go nuclear, in particular because they want to address their, the climate change mitigation issue. And they commit themselves for 100 years in the future. So these numbers are important because it demonstrates to the rest of the world that it's not true that nuclear is only for, the countries that they already have a nuclear power plant, that they just will complete their operation and then nuclear is over. According to this number, even if they are not very high, this is not true. So at the end of the day, if we consider the trends in a realistic or more optimistic way, these are the numbers. This is the low case. The numbers comes from some forecast that the International Atomic Energy Agency makes every year, also in collaboration with other international agencies. So if we consider that, for instance, we don't proceed with life extension, of course, there is both in between now and 2030, and above all in this time period, 30, 50, there will be a considerable number of nuclear power plants which will be retired. Okay, so there will be a shutdown of a nuclear power plant in the case in which we don't proceed, for instance, with a long term of operation and life extension. The additions, if we consider just the addition which have been announced, they even not compensate the retirement. Okay, so of course the low case is not really optimistic. It shows this decline in nuclear power plant, in nuclear energy production worldwide. But if we are more optimistic and we consider that actually some nuclear power plants, above all in OECD country, will be extended to 60, or someone also talk about 80 years of operation. Of course, the situation of retirement is much better, above all in this range. And then we can be even more, it's not related, but of course, if you consider that all these newcomer countries will also, the one which have just announced to go nuclear will, go ahead and will really take a commitment, of course, then we can even think that at the horizon of 2050, there will be more or less, double in the nuclear power plant capacity in the world. This is a transition slide to say that, of course, we are going to talk about advanced reactors. There will be no advanced reactor, in my view, contributing to all this picture, and in particular to the climate change mitigation, if we don't go ahead with the current fleet. The sustainability of the existing fleet is of primary importance. It ensures, first of all, that we keep going with the contribution to decarbonization of the electricity sector, which represents nowadays 1/3 of the whole clean energy produced worldwide. And also, of course, is a very important bridge for the nuclear industry. If there is no, I mean, if there is a decline in the use of nuclear power today, for sure the nuclear industry will not be ready to face this challenging realization in terms of SMR, microreactors, Gen 4 technology. Oh, this tightly coupled hybrid energy system, fantastic system in which we couple everything, and the system is a zero emission of CO2, and we put together all the possible carbon-free technology, and including, of course, the case of non-electric application. When we talk about advanced reactors, well, it's always my pleasure to show this slide, because it is our, meaning particularly, this database is managed by my section. We are responsible to provide up-to-date and detailed information on all the advanced reactors under construction or development worldwide, because when we say advanced reactors in IEA terminology means also Gen 3 and Gen 3 plus. So here you can find also EPR, AP1000, APWR, and so on and so forth. But you can find also, for the available data, also the Gen 4 technology. The data, the information comes from the vendors. So the vendors provide this detail. We don't invent, or we don't collect information from the web. They are very reliable data coming from the vendors. We just, of course, verify that there are no promotional statement, or that there is internal consistency in terms of technical information, but of course they come from the vendors and the developers. So I always launch this message that is very important to keep this database up to date, because this is also the database that we use when we go to the newcomer countries and we perform the so-called reactor technology assessment, which is another service provided by my section, in which we train, we don't give instruction, we train this, for instance, the so-called NAPO, to perform a comparison between different advanced reactor technology. We have a methodology and also a tool, very simple IT tool, which consists of a very detailed matrix. There are 19 major criteria and then a number of sub-criteria. And then we compose our matrix, and we can compare different technology with respect to the needs of the newcomer countries. Different newcomer countries, they have different needs. They have to decide what are the reactor technologies that they want to compare, and they have to instruct the IEA on what is important for you. And the needs are different in different parts of the world. And then we compare this with this methodology, we compare the different technology available on the market or near-term deployable technology on the basis of these criteria, and taking into account the needs of the country. So this is why it's so important to keep this database up to date. So it's a message also to the the company here that they are providing the different reactor technologies, because the data for this exercise come from the ARIS database. Oh, now talk about the SMR. Okay, well, I will be very, very short. I don't want. Well, this is the picture of the technology holders, okay, and which also show the big expectation in the near future. We publish this booklet, kind of dictionary of SMR every 2 years. Last year we published one with 56 SMR under consideration in the world. There are some which are very close to operation, like KLT 40 in Russia, but there are also others that are really at the conceptual phase. It was also very benign with my country. I put still IRIS. I don't know if someone here is still working on IRIS. Well, I put Italy. So just to say that actually there are also concepts that we are not very credible, at least for a near-term deployment. But the situation is pretty interesting. Look, for instance, Russia is known only for KLT 4060 and RITB 200, because they will be connected very soon. But look at the number of SMR of the different technologies that they are considering. The same US and other parts of the world. The reason why they are so interesting is because of flexibility, reduction in their shortening of the construction time, the fact that they should be shop fabricated and then transported to the site according to the demand. So it also from the financial viewpoint, in principle, are more interesting. First of all, because you reduce the construction time, and then because you don't need to install the whole capacity in one shot like with a big reactor. Okay, you can start with the first unit to be constructed, why not in 3-4 years, and then connect it to the grid, and then have already return from your investment, and with your return of investment to build another reactor, brought to the site, and so on and so forth. So from the financial viewpoint, they are interesting. They are also interesting because of their flexibility. They are more suitable than the big reactors to be, for instance, coupled with renewables. And because of their flexibility, they open the road to other possible application, for instance, in remote regions or in small grids worldwide. However, here I will not go through the whole things. There are potential technical and non-technical advantages among the ones that are the ones that are already mentioned. For instance, easier the financing scheme, or be particularly suitable for small electrical grid. However, we have also identified a number of challenges, and just because we were talking about the newcomer countries, it's clear that the major issue that any newcomer countries encounter in order to adopt SMR is the lack of operational experience. So since the country doesn't have an indigenous experience on the technology, of course it's very challenging for them to be the first to adopt SMR, which on the other side would make sense, because since they are normally these newcomer countries, they have also, they are developing countries, and they don't have actually the need of a big installation. Of course, SMR from this point of view are interesting also, of course, from the financing viewpoint. The IEA provides support to all the countries interested on SMR through this technical working group. In particular, it will be very important in coming years to develop generic user requirements and criteria, because at the end of the day, this SMR has to be operated by someone. So everybody talk about regulators, framework, etc. But first of all, we have to establish utility requirements. Otherwise, no utility will buy a single SMR. So this is the effort for us for coming years. However, we also address, of course, safety. We have established this Secretariat for SMR Regulators Forum, where there is Finland and France and United Kingdom from Europe. Europe, not the EU, because United Kingdom is still to be seen. These are the activities of our regulator forum. It's very, well, there is already a document for people who are interested, which makes the first consideration of the so-called graded approach on the defense in depth, and above all for this story of the emergency planning zone, because you know that the expectation for SMR is in particular the fact that the EPZ should be reduced, or even in some extreme cases also eliminated, while maintaining the fifth level of defense in depth, which is EPR, which is not the European reactor, but is emergency preparedness and response. This cannot be eliminated anyway, because it means that we are going to contradict what we have seen in the post-Fukushima analysis, that we have to strengthen the overall concept of defense in depth, also with a strong fifth level of the defense in depth. By the way, for your interest, there will be a technical meeting on next generation reactors in 2020, which is actually a follow-up of a meeting that we held in 2017. We'll talk about not only SMR, but also Gen 4 reactors, and in particular, the story of what is the possible impact on EPR coming from these new reactors. We also provide a big support on SMR to Europe through this big TC project, we have some European partner, let's say, in this big technical cooperation program, but unfortunately not very much, not according to the increasing interest in SMR also in Europe. So if you wanted to start looking at, this is a good mechanism to join the SMR community. The SMR, yeah, I just finished. I just want to say that, yes, since it was part of my presentation, I just want to touch upon the fact that there are also big expectations in terms of addressing the non-electrical part of the nuclear power production, which is the so-called non-electric application, and of course you can address all these applications also with the big reactors, but because of their flexibility, we think that SMR are more suitable for non-electrical application, and since there are SMR of any reactor technology, from water-cooled reactor to gas-cooled reactor, liquid metal-cooled reactors, very high temperature, and also molten salt reactor. Of course, there is the possibility, according to their evolution and progress, to slowly, okay, open the road to application at increasing temperature. So is a deployment which can go together with the development and deployment of the different SMR technology. I don't want to really, it was too long and short. So I stop here because I think that at least I touched all the main points of my presentation. I thank you very much and apologize to be so long.
Thank you, Mr. Monti, for the interesting presentation. I do not allow any questions. If there are questions, we can have it at the end of the session. So next presentation about innovative generation 2 and 3 reactors, fuels and materials will be given by Pietro Agostini. He's replacing Ms. Constantina Lambrino. He received his master in mechanical engineering at the University of Firenze, Italy. And since 1984, he is a scientist at NEA in the field of liquid metals experimental activities. He was and is coordinating several EU projects. I kept it short, so please.
Thank you. I start immediately due to times. I want to tell that this presentation collects 4 EU projects which have in common the fact that they are European studies to prevent structural material failures in reactors. It is aimed on structural materials. Il Trovatore is the first one. It proposes new fuel cladding materials able to resist to very high temperature, which are encountered in the loss of coolant accident in PWR reactor. The second is multi-metal. It's a project which collects and analyzes cases of dissimilar metal welding, which are a typical location for brittle fracture. The third is a matter project, which is related to liquid metal cooled fast reactor, where the material failure causes, besides high temperature and brittle rupture, are also corrosion attack, that is very important. The fourth project is SCWR, related to supercritical water reactor, and again, the failure causes to consider here are corrosion and high temperature. So this is il Trovatore, the PWR. In case of loss of coolant accident, there is a fuel cladding failure and the release of fission products. So arise the necessity to find some accident-tolerant fuel clads. This project is aimed on clad of fuel, and this clad have to outperform the common zirconium-based commercial proposal presently proposed. The project, Il Trovatore, has got 5 million euro from the European Union, and it proposes these new materials for accident tolerant fuel cladding, and also test them in a condition industrially relevant with irradiation, neutron irradiation in PWR-like water. The candidate materials are silicon carbide, coated commercial clads, surface modified by gas system and ODS. These are the different proposals which are tested in the project to find their behavior. The impact regards the Gen 4 reactors and also Gen 2 and 3 reactors in case of success, and beside that also some other industrial application. For example, it is mentioned concentrated solar power. The great hope is to increase the nuclear energy acceptance by general public. The Il Trovatore has also a good program in dissemination by a series of workshops and summer school. And second project is Multimetal. Multimetal got 1.78 million euro from the community. Is led by VTT Finland. The objectives of this project was to collect information, field experience on the dissimilar metal welds, address also numerical methods, and most important, comprehensive material testing program. The scope is to arrive to develop a test procedure for fracture toughness of dissimilar metal welding, and have a recommendation with the objective to achieve a leak before break behavior. These are some specimens to be tested. These are different dissimilar material welding, austenitic steel and ferritic martensitic steel, and the characterization and property benchmarking was the object of a program, of a project. This is a sketch of a CT specimen subjected to the toughness determination. The final results were in improved rules, understanding of the behavior in terms of brittle fracture, and it is recommended to improve the guidelines for fracture toughness testing. The third project is a Matter project, which got 6 million euro from the community. It is aimed to the use of ferritic martensitic steels for two ESNI reactors, Mirra and Astrid. The main achievement of this project were the development of guidelines and standardized setup for the testing in corrosion environment, experimental demonstration of liquid metal embrittlement of the ferritic martensitic steel in the heavy liquid metal, recommendation for design rules of a grade 91 steel in different conditions, ratcheting, creep fatigue, negligible creep, weld, and weld coefficients. All the proposed design rules were submitted to AFCEN. Here there are some examples. In particular, it is important this picture which shows the brittle fracture of a specimen in heavy liquid metal. The dissemination was quite complete of the information because all the experimental data were loaded in this repository at JRC, MathDB repository. There had been a workshop and summer school and a special issue in the Journal of Nuclear Materials with this work. This is a sketch of the contribution of the different countries to the dissemination. So the impacts of the project were the exclusion of grade 91 steel from the MIRA project, and also its downgrade as steel for the heat exchanger of Astrid. These were due to the liquid metal embrittlement, unpredictable behavior of welded joints, and the poor steel fatigue resistances. So this project has triggered a new R&D initiative on different paths. Austenitic steel, resistant to corrosion, and protective coatings, as well as ODS. The last project is SCWR. SCWR has got €1.5 million from the community. It is a collaborative project with Chinese partners. The main the main challenge was prediction of a heat transfer, choice of material for fuel and core structure, that is of our interest, and the larger uncertainties, technical uncertainties, were related to the evaporator of a supercritical water reactor, where the highest heat flux is present. The objectives of the project was the design of a supercritical water loop to be coupled with a test reactor in Czech Republic. Also the analysis of the behavior of this water loop, and construction of a test assembly simulating electrically the supercritical water loop. This was made by the Chinese side. Validate codes, and finally focus on material research for the cladding materials. And the pre-operational safety report was a result. This is the water loop coupled with a small reactor this is the active channel in Czech Republic. These are calculation of temperature. This is again the system. Okay, these are the data related to the material choice. 316L was selected as the most appropriate material. This is the electrical loop made in China by the Chinese partners. So conclusion, the four projects dealt with material studies aimed to the safety of nuclear reactors. Il Trovatore was focused on the fuel cladding able to survive a very high temperature. Multimetal optimized the fabrication of bimetallic welds, which are potentially prone to the brittle rupture. Matter has evidenced important issues in the ferritic martensitic steels when used in harsh liquid metal environment, mainly the heavy liquid metals, and many other researches were triggered. And SCWR identified the best performing material in terms of weight loss, which is a connection of corrosion and erosion in a supercritical water reactor. So, thank you.
Thank you, Mr. Agostini, and for the precise talk. Are there any questions? No, there's none. May I ask a simple question? I've seen the temperature of 550 degrees within the last project. Why is this temperature selected?
Where? FISA?
Yeah? No. Back. Yeah, the peak fuel cladding temperature was 550 degrees in this.
Which project?
The last one.
The one?
Next.
Yes.
Yeah, here. And it's also mentioned on the other slides. Can you give me an idea why it is 550 degrees?
No. I'm sorry, I'm not expert of this project. Probably.
This is actually the temperature we are reaching in the concept that we are today working, because all those material research for Gen 4 systems, we are addressing Astrid and Mira. And the working temperatures, that the peak temperature of our clad will be that temperature. The temperature of the fluid is lower, but that's the hottest.
But even though this is a SCWR project, so you can see some cross-cutting between SCWR technology and liquid metal technology, which a representative of the Commission are always looking for.
Thank you very much. Thank you. So let me introduce Mr. Stefan Valans. He has a PhD in numerical method and material science. He has worked in several places, from Austin in Texas to Switzerland, and is now at SEA, working on behavior of reactor fuels, responsible for the LEU Forever Horizon 2020 projects. Stefan, the floor is yours.
Thank you. So my presentation today is on innovative and safe supply of fuel for reactors. I'm doing this presentation also on behalf of Bruno Baumeister, Winfried Petri, and Jan Oglund, who are coordinators of other projects that I will introduce later on. So first of all, just to set up a little bit of context that this here everybody knows about, research reactors and nuclear power plants are the key element of a working ecosystem for nuclear power usage. And the interest is so decarbonated electricity supply, of course, but also, for instance, for research reactors, production of medical radioisotope and high-level science. Now, if you want working NPP or working research reactor, you, of course, need a fuel element. And this fuel element is provided by a fuel provider who basically will take depleted uranium, enriched uranium, structural element, and manufacture a fuel element. And this fuel element will meet some requirement by the nuclear power plant and research reactor, which are given neutron flux in normal operation, safety in incidental and accidental operation, and also cost effectiveness, of course. Here, the three projects I'm presenting have challenges in 2 points for the fuel provider. One is diversifying the suppliers. So it's typically the case for Russian technology reactors who only have one supplier for their fuel. And the second point is to innovate to reach non-proliferation goals, and this targets particularly research reactors, high-performance research reactors, but I will come back to that. So fuel supplier diversification. So for some design of research reactor and NPPs, you have a historic fuel manufacturer from Soviet and so now Russian origin. It's for NPPs, it means VVER technology NPP. There is quite a number of issues linked to a unique fuel provider, and it's quite quite rapidly you can think at what happens if the provider defaults. There is no incentive for continuous improvement of the fuel because you have only one provider, so there is no concurrence on the market. And for the same reason, you do not necessarily meet cost effectiveness. In Europe, and this concerns for NPPs, VVR 4040 from Czech Republic, Finland, Hungary, Slovakia, and Ukraine. For research reactor, this concerns Czech Republic, Hungary, Poland, and Ukraine. If you want to meet fuel supplier diversification, you have a couple of challenges to meet. First one is to analyze the key function. So you have to do reverse engineering on the fuel that already exists. You have to reproduce the normal operation behavior. You have to preserve and improve the key safety feature. And you have to propose a cost-effective solution that you can manufacture also. Key points to reach this goal are the collaborative approach, including manufacturer, research experts, reactor operator. Also, you have to improve safety and operational feature of the fuel elements, and to include the preparation of the licensing steps as soon as possible. For research reactor with high enriched fuel, so the question here is not a question of diversifying the suppliers, but to meet the target of the Global Fleet Reduction Initiative, where it's stated that your fuel enrichment should be below 20% to 35U. This conversion has already been done for a medium performance research reactor and is technically feasible and ongoing. Now, the last research reactor that remains to be converted are the high performance one. So the challenge is to use a fuel below the 20% enrichment while conserving the reactor performance and to prove and improve the reactor safety usage. So the three projects I'm presenting today are meeting these goals. So SNF project, European Supply of Safe Nuclear Fuel, and LEU Forever are both dedicated to the diversification of sources of fuel supply for VVER and research reactor. Whereas LEU Forever and Heracles CP targets also the development of non-proliferant fuel for high-performance research reactor. You can find on the slides a website for each of these three projects, and I, of course, invite you to visit the website. Okay. Now, how did this challenge? How are this challenge being tackled? First, to be cost-effective, an approach which is called design to cost has been put in place. So this is typically for the medium power research reactor fuel supplier diversification, where you input the generic fuel technical requirement and then work together in the different fields necessary to design the new fuel. You work in a continuous manner to reach a generic fuel preliminary design that meets the design to cost approach. For SNF project, there were also the same kind of approach was used, where design inputs organized around workshop was done. Particularly, there were workshops on fault analysis, fuel rod design, thermal hydraulic design, and nuclear criticality safety. And there was also an extended use of scientific calculation with code coupling and CFD models. With respect to low enriched uranium fuel conversion, we have right now at hand mostly one effective solution, which is uranium molybdenum fuel, which enables to reach a high enough density of 235U in the fuel. Basically, this is a curve of uranium density versus uranium enrichment. Actual high-performance reactor in Europe are between, let's say, 80% enrichment and 27. The target is to go below 20. And for this, uranium, molybdenum, or U3Si2 with high density are the preferred solutions. In the LEU Forever project and the Reckless CP, there is a number of advanced tests which are foreseen. So particularly the Semper Fidelis irradiation, which is an irradiation testing the uranium molybdenum fuel capacity. The Empire irradiation, which is done in the US, so not not funded by the Europe, which targets monolithic fuel comprehension, so uranium molybdenum monolithic fuel. And finally, this will lead to a final irradiation Ifeter-3 and Feter-mono-1. In terms of results, so for the SNF project, it resulted in a new VVER 440 fuel design with an optimized zero cladding. The fuel road has been optimized with 3D neutronic calculation, and the design was done so that inspection and repair were possible on the new design. Concurrently, there was an assessment of manufacturing capabilities, and it was estimated that a time frame of 24 months would be necessary to establish a full production chain, and 24 months were also necessary to license fuel transport containers. For the medium power performance research reactors, there is so several workshops have been organized within the LEU Forever project. Resulting from this workshop and the work from Technicatom, a preliminary design was proposed, and you can find several communication on this preliminary design in the RRFM of this year. Finally, for low-enriched uranium conversion, so the Semper Fidelis irradiation campaign reached its end this spring. So 11 plates total were irradiated. One plate with a 4-cycle showed no failure sign, so this is a very encouraging result. And within LEU Forever, depleted uranium plate for high-loaded U3Si2 were manufactured, and also the proven feasibility of gradient monolithic uranium molybdenum fuel on surrogate material was done. Okay, so this is a compilation of all the communication that have been done within those 3 projects. And to finish with, so the objective here was to secure the supply chain of nuclear fuel, both for NPPs and research reactors, and to reduce the proliferation threat with respect to low-enriched uranium fuels. The main achievement are the design of a replacement element for VVER 440, test of reliable conversion fuel for high-performance research reactor, and the design of a conversion element for medium power research reactor. Thank you.
Thank you very much. Are there questions? Yes, please.
Jan Valenius from KTH Stockholm. You showed the composition of the research reactor fuel, which seemed to contain zirconium nitride. What is the function of the zirconium nitride?
Yes, so what you can see here is a typical dispersed uranium molybdenum fuel. So you have a molybdenum phase dispersed in an aluminum matrix. And one of the problems with this is that you have a tendency to form an interdiffusion layer between the uranium molybdenum particle and the aluminum matrix. And this interdiffusion layer is really bad, so to say, when coming to efficient gas retention and mechanical properties. So different solutions are being tested to prevent the formation of this interdiffusion layer, one being the use of zirconium nitride coating on the uranium molybdenum particles.
Okay, thank you very much.
More questions? Yes.
Thank you for your presentation. I have a question concerning the LEU. You have not really mentioned it. You just in your conclusion, you say that you have done research on the dispersed and on the monolithic. So how is the situation, and do you see any, how can I say, development also in the monolithic type of LEU fuel?
Okay, maybe it was not very clear in the presentation, and I excuse myself for that. The LEU Forever and Heracles CP project both have a component where they look at monolithic fuels, so uranium, molybdenum monolithic fuels development. This concerns particularly the TUM FRM2 reactor. So this is a preferred solution, conversion solution for TUM FRM2 reactor. Now for the status of monolithic UMO fuel, the results we have been obtaining up to now are really encouraging. So we have proved that we can manufacture such a fuel, that we can use it, but we still need irradiation test outcome to be sure that it's a really working solution.
Any more questions? Can I ask one, if you mind? Why did you concentrate on VVR 440 fuel and you didn't look at VVR 1000 or 1200 fuel, since this is the new type of reactors that we are having in Europe?
Okay, I will try to answer at the best of my knowledge, because this is definitively not my project. What I understand is that VVR ER 440 is a type of VVR that is present in Europe. So I guess that the point is mostly this one, is a replacement fuel for reactors that are present in Europe, from what I understood.
Okay. Thank you. Thank you very much.
I just would like to add something, because I was a project officer who was at their evaluation, and we did have both proposals for evaluation for VVR 440 and 1000, but for 440 was better written, so it won. It's one point, and second point, as you apparently know, I think right now is quite a big experience with 1000 in Ukraine. As far as I know, they moved to the mixed active zone, and recently even only to the active zone from Westinghouse fuel. Whereas with 440, they used to make it for Finnish plant, but they abandoned 10 years ago. So I wanted to revive the whole procedure. Also, on the other hand, you are correct, there is a very low chance for the business case for 440 for Europe, because they are phasing out. And newly built most likely will be 1000 or 1200, so kind of a bit of contradiction, but again, this was a fair competition in our call, a result of fair competition, and the project was quite well done.
Regarding the VVR 440, as you said, they are phasing out. It's not exactly true, because now there was, for example, long-term operation for another 20 years in Czech Republic, and I think this is the case also for Slovak and Hungarian power plants. So they are still commercially attractive. And maybe one more information about what VVR 1000. There was example from Ukraine, and in Temelin there is now, I think already in the Korda 6 lead test assemblies. of Westinghouse. Again, example. Okay.
Okay, thank you, Stefan.
Thank you.
Now we're coming to the last talk before the coffee break. The talk will be given by Dr. Ahmed Bentay. He obtained his PhD in 1993 in applied mathematics in Lyon, France. He has more than 20 years experience in hydrogen risk issues and safety licensing. And currently he is an expert in nuclear safety at IRSN, in charge of R&D and safety assessment. He coordinates the Mitigene project, which is funded by the French agency and the Samconet under Nugenia umbrella. So you will.
Thank you,
It's
Mr.
your
Chairman,
fault.
for this kind introduction. Good morning, ladies and gentlemen. My talk is about severe accidents. It's somehow different from the previous talk. And when we talk about severe accidents, it means that we are in condition to have a core melt and the possibility of a reactor vessel rupture, and also the possibility to have combustible gas release inside the containment with the possibility to have hydrogen and carbon monoxide explosion. This is basically what happened in Fukushima Daiichi. And also the fission product release inside the containment, reactor containment, and outside. This is, I will do my best to present you the main outcome of 6 projects dealing with this different topic addressing severe accidents, means core behavior inside the inside the reactor vessel, and also what happened inside the containment, and how we can reduce the source term release outside the containment. My co-authors are the coordinators of this project. I have to mention here that I was not involved in any of them. This is, please be kind with your questions. I will do my best to answer your questions. So, as motivation, this Fukushima Daiichi accident, after this accident, the stress test performed in Europe and outside Europe underlined the need of further investigation to improve the severe accident management strategies, including external hazard. And many of the recommendations of this stress test was to upgrade the existing nuclear power plants by implementing new devices as recombiners or containment filter venting systems. And to achieve these goals, basically, there are 2 ways to do it. The first one is to fill the gap of knowledge and to reduce the uncertainty related to this phenomena participating in severe accident. This is basically what was addressed in the framework of ALESA, SAFEST, and EVMR projects. The second way to achieve these goals is to develop new mitigation systems and strategy to reduce the source terms. Source terms means what could be the fission product released outside the containment. And to ensure the heat removal, basically where we are in condition of station blackout, when we lose the ultimate heat sinks, how we can develop system to ensure somehow this heat removal. This is basically what was addressed in the framework of Hassan project and also as CO2 Hero project. Of course, all this knowledge coming from experimental data performed in this project had been hosted in. We had to capitalize somehow this knowledge in tools, in safety tools, and this was the objective of CESAM project, is to improve the modeling of severe accidents and the severe accident management of ASTE code. ASTE code is really the European code for severe accidents, and to make it to improve the ability of this code to address also different design, including PWR, BWR, VVR, and can-do technologies. So I will give you an overview of each of the 6 projects, and I will not go in details, it's only the main outcome of each of them. I will start by what happened during in the reactor vessel, and the first project is safest project, the acronym of Severe Accident Facility for European Safety Targets. The objective of this project, is coordinated by KIT and the consortium. You have many partners from Europe, but not only. You have also the connection with the Japanese colleague, with this CLAD laboratories created after Fukushima to deal with Fukushima Daiichi decommissioning. And the objective of this safest project is to create an integrated pan-European laboratory for severe accident research. The idea is to have a common vision on what are the most important issues regarding corium research and to deal with. And of course, within, to develop a research roadmap on this issue and to establish access to safest research infrastructure to perform experiments dealing with core degradation in vessel and ex-vessel melt situation. And also in frame of this project is also to increase the ability or the knowledge of and the instrumentation and quality of R&D of these experimental infrastructures. The main outcome of this, of course, I forgot this. The safest project allow, as I mentioned before, the development of roadmap. This based on the roadmap, 2 calls for proposal were launched in 2015 and 2016. Altogether, within these 2 calls, 16 experiments or experimental series had been performed dealing with different aspects of corium behavior, characterizing the corium properties, fuel coolant interaction, and MCCI. Different topics were addressed in frame of this performed experiment. Of course, this performed experiment are useful to improve the modeling of implemented in safety tools. The second project is ALISA, is basically adopted the same approach. The only difference is at the connection between Europe and China. There are 2. This project is was also coordinated by KIT in Germany, and 2 partners from Europe, KIT from Germany and COA from France, was involved, and 6 partners from China, including academic research institute and also industrial. And the idea is to allow the access to a large infrastructure dealing with not only corium behavior but also hydrogen dispersion and combustion within large facilities. In framework of this ALISA project, 2 calls for proposal were launched and experimental were performed dealing with core degradation and vessel melt behavior and retention, fuel coolant interaction, containment and hydrogen behavior, including dispersion and combustion, passive system, and also corium properties. The results are very valuable for code and model development. And based on this, the results coming from these two projects and from the previous new project, AVMR, dealing with investment retention strategy for higher power reactor was launched in 2015 with the participation of more than 23 partners coming from Europe and from Asia. And the main objective of this project is really to see how we can avoid the reactor vessel ruptures. The idea is to ensure to cool the external surface of the reactor vessel, and of course to extract all the heat fluxes produced by the corium, is to ensure that the critical heat fluxes outside what we can extract from this surface is higher than what could be produced during by the core melt. And the methodology initially adopted for low power reactor is really to ensure that we can extract higher heat fluxes, and to do that, the approach is based to make a balance between the produced heat flux here and what could be extracted at steady state. And in the framework of this AVMR project, it seems that during the transient, the heat flux may be higher than the heat flux what we could have during steady state. And during in the framework of this project, the methodology had been revised to take into account these transient conditions, and based not only on the balance between the heat flux inside and outside reactor vessel, but on the criteria based on the residual thickness of ablated vessel, and which is supposed to use safety code and the mechanical code to do that. Of course, this project is still ongoing, and still issues regarding this stratified condition what we can have during this transient, which are responsible of high heat fluxes. And the work is ongoing to deal with this issue. Now I will move to what happened in the containment and dealing with the PASAM project. PASAM, the objective is to improve system to limit radioactive release outside the reactor containment. This project was coordinated by RSN with the participation of 9 partners, including research center and also industrial, you can see here. And the main objective was double. The first thing is to explore what could be the way to enhance the existing mitigation system. I mean, for the moment, all the containment filtering system is based on either pool scrubbing system or sand bed filters. And the idea is to see how we can improve this mitigation system. For example, for the pool scrubbing system is to maintain the outcome of this project, to maintain a higher pH, to avoid any late iodine release. And for the sand bed filters, as we have in France, the possibility to add metallic prefilter to enhance the efficiency of filtration. On the other hand, it was also the opportunity to investigate the ability of innovative system to achieve large system attenuation by using experimenting new devices dealing with acoustic agglomerator, which means that that small particle will be we try to make it more bigger are the particles is the filtration is, and also experimenting also zeolite component to deal with iodine reduction release. If we look to this main outcome of this PASAM project, this project allow the production of a large database for existing and innovative mitigation system regarding gases iodine retention, either molecular or organic iodine, regarding hydrodynamics for scrubbers, and also long-term stability of trapped component. This project also allow a deeper understanding of the phenomena underlying their performance. They allow also development of sample model and correlation, which were implemented in Aztec code, and also have an estimation what could be the order of magnitude of the system reduction for each filtration system. So this is for PASAM project, and all the knowledge gained from this safest, ELISA, EVMR, and PASAM, the lesson learned was used to improve the model, European Aztec, European code for severe accident Aztec code, developed by RSN. This project was coordinated by GRS in Germany, and allowed the improvement of and the validation of the Aztec code, and to also improve the ability of Aztec code to be connected to a dispersion, atmospheric dispersion tool to be used for emergency configuration, and also to investigate to evaluate the severe accident management guidelines. Within the work performed in framework of this CESAM project allowed the validation of most physical phenomena with this new version of Aztec to produce a generic nuclear power plant input deck for this for Aztec community with different reactor design. The last project is dealing with heat removal, and the objective is developed a proof of concept which of this device, which could be plugged on the. Sorry, I forgot to mention that this project was coordinated by Duisburg Essen in Germany, University in Germany. The idea is to develop a device which could be plugged in the circuit and allow the heat removal. This device is based on Brighton cycle, using this supercritical CO2 as a working fluid, and allow this working within the extracted heat will be used also to produce electricity more than needed, and this additional electricity could be used to recharge batteries needed in case of station blackout in nuclear power plants. Within this project, a prototype was developed and designed, and the evaluation of a stick head was performed. The quality assurance has been demonstrated within this loop, and this safety code was used to evaluate this, the benefit of this device. And of course, as I mentioned before, the proof of concept has been performed during this project, and now the follow-up of this project, calling now is CO2 NPP, which is coordinated by EDF in France, has the objective to upgrade this technical readiness level from 3 to 5, which means that we are dealing with pre-industrial devices. So let me summarize my presentation. The main achievement of this project is allowed a better understanding of the severe accident phenomena, such as core degradation, core melt, and hydrogen deflagration, and contribute significantly to reduce the relevant the related uncertainties. In framework of this project, we have development of novel mitigation equipment for heat removal, the improvement of innovative strategy in support for the in-vessel retention and the source term reduction, the improve of the ability of the ASTIC code, and in framework of this project, also effort had been made for knowledge dissemination and education. Many PhD were involved in this project, and the demonstration prototype of this removal heat device was installed in a PWR glass model in Essen in Germany for teaching. Production of a large number of numerous peer-reviewed publication, organization of several workshops, and also participating to AEA and OECD projects within this state-of-the-art report or contribution to IEA CRP. So I would like to take the opportunity to thank the financial support on behalf of my co-authors, the financial support of Europe. Thank you for your attention.
Thank you much for the presentation. There are so many projects, it's hard to get an overview on all the projects, but are there any questions? Oh, there are many questions. Let's start with you.
Frank Carré. Thank you for your very comprehensive presentation. You mentioned the fact, well, the significance of supplementing the existing database and also the working towards reducing uncertainties in understanding basic phenomena. In addition to, I think, reducing uncertainty in combining, let's say, phenomena that have been investigated on separate effect experiments. Do you think that let's say the progress of numerical simulation or let's say artificial intelligence might help, let's say, better focus future, let's say, experiments, and maybe, let's say, to identify some time where more analytical type of experiments will be needed than really corium experiments with large amounts of corium?
For sure, the uncertainty, the effort has been made to reduce the uncertainty, still windows to improve, to reduce again this uncertainty. And there is a new project called MUSA and coordinated by CIMAT in Spain. We're dealing with this topic. The idea is how we can reduce the uncertainty when we couple this complex phenomena dealing with the severe accident. Of course, they still need, if I understand well your question is how we can use artificial intelligence to design new
analytical experiments than, let's say, integral experiments with large amounts of corium.
Yeah, which, if I understand well, it's before doing this, we have to have maybe a complete picture on the behaviors of the coupling between these phenomena. And I guess that we are not able now to do it, to replace virtual intelligence by new experimental data.
Okay, there's one more question.
Another question concerning a severe accident, IVMR project. You indicated that you tried to reduce the degree of conservatism. How well did you succeed? In the methodology of corium formation and the rupture of the reactor vessel through concentrated heat flux.
Yeah. This project, EVMR project, is still ongoing. And what I mentioned here, that the methodology has been revised to use as criteria not only the heat flux balance between inside and outside the reactor vessel, but based on the residual thickness. And the main challenges now is regarding when we have this inversion of corium metal layers, and this which drive a high fluxes, which is really challenging, and they still work on it. And what I heard from the coordinator, that they are working with the new experimental data to learn more, develop more, and enhance these models.
Okay. Is there any urgent question? I hope it's a short one. It will be the last one.
Well, it is a short one, and it's kind of a specific one, so I understand if you do not know the answer offhand. It's related to computational aids that are used for severe accident management. So what are the criteria that are used in Europe for core quench calculations?
I have to say that I don't have the answers.
That's fair. And the other question is related to, to Aztec code. So is it also the alarm parameter code? And how many nodes would you, no, it's not, somebody is shaking their head.
Aztec is lamp parameter code.
It is a lamp parameter. And how many nodes do you have for simulation of the core?
I'm more familiar with the containment. For the containment, we use basically from 20 to 80 nodes. And for the core, I have to check. Sorry.